So question 4 is about electricity around the home and current electricity. So it starts off by telling us that some ceiling lights in the home are connected to the mains by a 2-core cable. So here you have the diagram, you have your wire, your insulation, and then the shielding around the outside. Suggest why some ceiling lights do not have an earth wire. So this is because there is no metal casing. So it's usually made out of plastic, or you could say it is double insulated. So there is a little chance or no chance of an electric shock. So we don't need that earth wire. Next, write down the equation that links charge, flow, current and time. So we need to remember this. This is one of the ones we need to learn. So charge flow is current multiplied by time. If you were to write Q equals I times T, that would also be acceptable. So Q for current, capital, I, capital again, for current, and T for time. So Q for charge, I for current, T for time. We have a current of 2.95 amps in one of the copper wires for 60 seconds. So we'll use this equation again, Q equals I times T. I is 2.95, 60 seconds. $177, and the unit will be coulombs, which they've very nicely given to us already. Next one, figure 7 shows a current potential difference graph for a piece of copper wire. It's asking us to draw another line on figure 7 for a wire with a different resistance. So loads and loads of people always make the mistake of trying to draw a line at right angles to the first one, going through these two quadrants, so these two parts of the graph. We cannot do that. There are two marking points. The first one is for a line with a positive gradient, so it needs to start down here and it needs to move upwards like that, has to be straight. And the second marking point is that it goes through the origin, so when the potential difference is 0, the current is 0. So if I dig out my ruler and I'm choosing to do one with a gradient higher than the original line. It doesn't have to be higher, it can be lower, so you could have drawn it like this instead, but I've chosen to draw it like this, and that will get me 2 marks. Again, positive gradient through the origin. Some fuses have a thin piece of copper that melts if the current is too large. It's called a fuse. So a fuse essentially is our rectangle for a resistor with a line going all the way through there. Best if you draw it with a ruler, unlike what I did. Describe how the movement of copper particles in a wire changes when the copper melts. So it starts off as a solid where you have a regular arrangement of particles. They are in contact and vibrating about a fixed position. When it melts, it becomes liquid, where you have a random arrangement where the particles are free to move about each other. Free to move about each other. 4.7. All copper wires are melted when they are recycled. Calculate the energy needed to melt 500 kilograms of copper at its melting point, and specific latent heat of fusion is 200 kilojoules per kilogram. So they're trying to catch us out here by putting this kilojoules thing here. So what I'm going to do is multiply that by 1000, and that's going to give me 200,000 joules per kilogram. Now if we hadn't spotted that, we'd have lost at least 1 mark when we went to do our calculation. So if we were to look at the physics equation sheet, we'd see that the energy needed to change state is mass multiplied by the latent heat of, or specific latent heat of fusion. So that is 500 multiplied by 200,000 is 1 with 1, 2, 3, 4, 5, 6, 7, 8 zeros. So we could write so 1, 2, 3, 4, 5, 6, 7, 8, too many zeros, or 1 times 10 to the 8 joules. So quite a lot of energy there.